There is a movie called I, Robot, but it has a really nice exchange between Will Smith and the robot in the movie. The robot, which is an example of AGI, has been caught in some crime, and Will Smith is the policeman interrogating it. And he asks it that, you're just a machine, what do you know about, can you paint a sunset? Can you write a Shakespeare sonnet? Can you, write a song or a symphony? And the robot replies to him and says, can you? And this is true. There is a significant overlap between what humanity, all human beings can do, and what AI can do already.
True.
Already AI can do a lot of things that I can't. I can't write a symphony, but there are models out there that can do this. If I want to look at smaller and smaller things, I need to go to higher and higher energy. So it's one thing for me to say that, okay, I want to look at an atom. But then it's something else to say I want to look inside a proton and then inside a quark. Each of these requires you to go to higher and higher energies. In some sense, this is what any particle collider is meant for. Today, the world's largest energy collider is the Large Hadron Collider, which is at CERN in Geneva. It collides two beams of protons. The collision energy right now is 13.6 TeV in some units. The idea behind these accelerators is simple. You take these fundamental particles, you give them a lot of energy, and then you collide them. Now, most of the listeners will know Einstein's famous equation, E equals mc square. So once I have this amount of E, I can create the equivalent amount of m. And so then what we hope for is that from these collisions, we are able to create other particles, let's say. Now, other particle means not just the stuff that we know about, but also the stuff that we haven't discovered so far.
Joining Once Changing the World, India's first Future Tech meets Sustainability podcast. I'm your host, Eddie Avel, and today I'm delighted and honored to have with me Professor Saurabh Dubey, a physicist at IISER Pune and a key member of CMS, the Compact Muon Solenoid Collaboration at CERN. His work involves searching for new particles beyond the standard model of physics and forces that could solve some of the deepest mysteries of the universe, including the nature of dark matter and mini black holes. He, along with Professor Seema Sharma, is a recipient of the 2025 Breakthrough Prize in Fundamental Physics. So, Professor, really appreciate you taking time and being part of the podcast, and congratulations on this incredible and well-deserved honor. So, wanted to start with the origins of the universe, since your work is at the Large Hadron Collider, which is essentially about recreating the conditions of the early universe. It will be great if you could take our audience back 13.8 billion years ago, from where it all started, the Big Bang.
So this is like an interesting joke. There's this show called The Big Bang Theory, which has a character called Sheldon. And if you ask him any sort of a physics question, he always starts by saying, okay, let's start at 13.8 billion years ago. And then he wants to tell you the whole story. Um, One thing I'll say is that it's interesting how typically students, when they just start learning physics, they draw all these boundaries amongst the different subjects, right? Something is cosmology, astrophysics, particle physics, and so on. But nature, of course, doesn't have any boundaries. So how the universe started off is a story that sort of spans across a bunch of different ideas, primarily, of course, astronomy, um, where we started off with these observations that galaxies that are far away from us tend to be moving faster away. This sort of led to the belief that, okay, if things are moving faster away, that means at some point they were closer to each other. And then, of course, you can do some measurements. You can measure how fast away something is moving, and that depends on how far away it is from you. And so you do all of that, and that makes you believe that the universe wasn't always the way it is, but that it started at some point. And so that's what the Big Bang hypothesis is. It says that if you just try to trace back what you see today, it goes back and it maybe started from a point. Now, this is kind of a weird thing to sort of believe in, right? Like everything started from a point, because in this case, we actually mean the geometric point. Like it actually means it started from a single small place. And what is even more weird about this is that then people have this notion of thinking that where is this place? Like where did it start from? Turns out that is everywhere. So, it just, this is the center of the universe and that is the center of the universe. It all started from the same point. Everything was there. That story has now been verified fairly well with a bunch of different telescopes and very detailed measurements of a bunch of different things. So not only do we measure how the galaxies move away from us in different directions. There is also this thing called the cosmic microwave background. This was a very interesting discovery. It just happened. There were a couple of people who were trying to do a different measurement, and then they thought they heard some noise in their equipment. They did everything under the sun to reduce this noise, but it turns out that this background noise, so to speak, or this radiation, is everywhere around us. You can point your radio antenna at any direction or your microwave antenna at any direction, and you get the same level of noise from everywhere in the sky. And in some sense, that is the echo left of that original Big Bang. That's how we try to do this, and it's that also makes us believe that since it is everywhere, that's why the universe expanded from that point. It exists all around us at all times. So that's how I'd say things actually started off. Then of course you need to fill in all the details, like, okay, sure, that's what I think, but what started off? Like, did we have atoms beforehand? Did we have protons? Did we have quarks? How did the quarks come together to form protons? How, at what point did we have hydrogen? And then much later, at what point did we have stars and galaxies, and so on? That's where a lot of the particle physics sort of seeps into cosmology.
So very interesting. I don't have like much background in the education. I dropped out of the college, but I was always curious about the nature of reality. Like where did we come from? How did like everything start? I mean, then I just read a little bit and kind of understood that it all started from Big Bang. And like you said, I mean, the general assumption is that it started from a point of like maybe possibly nothing, and then it's ever expanding universe of ours, and in that we kind of exist. And it's basically this mixture of these particles and these four fundamental forces of nature, which is the strong and weak nuclear energy force, gravity, and electromagnetism. And when it all binds together, it gives rise to this complex thing that we see, the universe, and everything around it. So it is so fascinating. Wish I could have been part of CERN, I mean, to be, because that's where I think people go to kind of understand the nature of the universe itself. This Large Hadron Collider at CERN, Geneva, that there's 21-kilometer underground tunnel where you kind of, push these particles and shoot them at the speed of light, and kind of meets and creates this energy, and you try to kind of learn from that. So how fascinating. And you've been doing this for the longest time. So I gave a very very crude maybe this of what like the Large Hadron Collider is, but it'll be great for the listeners who don't know what the Large Hadron Collider is. Will be great if you could give us a lowdown of what is the Large Hadron Collider, the sheer scale of this machine, and what fundamental question was built to answer.
Okay, so once again, so the idea itself is crucially simple. If I want to know what something is made out of, I try to break it apart, and then I look inside it. This works for, if I have a piece of chalk, I'll break it apart, I'll get a powder, then I'll try to break that apart. At some point it turns out that breaking apart things requires you to have more force than the force with which those things are stuck to each other. This is where having collisions comes in. So at some point you realize that, okay, I can't just take my metaphorical hammer anymore, but I need to start to smash these things at higher and higher energies. This is also sort of connected to one other idea. In some sense, energy is connected to length. Um, Typically, de Broglie wavelength is the thing that if people want to look up. But what this means is that if I have want to look at smaller and smaller things, I need to go to higher and higher energy. So it's one thing for me to say that, okay, I want to look at an atom, but then it's something else to say I want to look inside a proton and then inside a quark. Each of these requires you to go to higher and higher energies. In some sense, this is what any particle collider is meant for. Today, the world's largest energy collider is the Large Hadron Collider, which is at CERN in Geneva. It collides two beams of protons. The collision energy right now is 13.6 TeV in some units. Uh, but we've had colliders before this. Even CERN had the super proton synchrotron, and the place where I got my PhD was the Tevatron, which was at Fermilab in Chicago. And so the idea behind these accelerators is simple. You take these fundamental particles, you give them a lot of energy, and then you collide them. Now, most of the listeners will know Einstein's famous equation E equals mc square. So once I have this amount of E, I can create the equivalent amount of M. And so then what we hope for is that from these collisions, we are able to create other particles, let's say. Now, other particle means not just the stuff that we know about, but also the stuff that we haven't discovered so far. So now that's nice. So if you do enough of these collisions, then occasionally you're going to produce something new. Then it is up to how smart you are to figure out that, oh, what you're seeing is something new, not something that you have already found earlier. Um, Now, of course, this is simplifying the thing quite a bit. These colliders are rather hard to build because a proton is actually a very small object. So, different kinds of analogies spring to mind. One of these analogies that gets spoken about is that if you want to collide two protons, that's like trying to take two needles across a distance of 10 kilometers and sort of making sure they hit right each other like this. So it's very difficult. You have to develop a lot of allied technology for this to work out. There is a lot of work that happens in basic electromagnetism theory, like how do you build magnets that will be superconducting and they will sustain the currents of these protons. They need to work at these high energies. They need to be able to keep the magnetic field at the precise value that you want. It can't drift higher or lower. And so that's also a technological challenge. You need to build this equipment, right? It's no longer a pen and paper thing, but you actually have a beam. You have a machine that's doing this, which is where a lot of the I would say credit of CERN goes. That you have a bunch of smart people who've managed to come together to build something that actually works. It's been collecting data for more than for a long time now, 2009 onwards, and at various different energies. So we didn't always collide at 13.6. We started off at slightly lower energies, and then we've built up to this. And so that's the idea, that you take two things, you smash them together with two goals in mind. One, I want to peek inside it. So if I can break it apart, I'll see what's inside it. And the other thing is, with all of this energy, E equals mc square, I can, prepare new things. And so then the idea would be to look for these new things.
Right. How exciting. So, Professor, I mean, one my question that comes to mind is that we have like a 21 kilometer this long underground
26. So
tunnel,
it's 26 kilometers.
26 kilometer underground tunnel, but it's still we don't kind of understand what the universe is made of, because I mean, still we don't have possibly the enough energy and what would it take for us to create a tunnel, maybe possibly which is large enough, which would give us the complete insight of the Big Bang, because I mean that's what the entire study is about, to kind of understand how the kind of universe came into being and all the particles and things like that. How long a tunnel, what kind of forces, energy that we might need to kind of understand like the entire universe, and second is like the standard model of physics, because we've understood, I mean, the standard model of physics, there are like there's a bunch of particles in there. Will be great if you could kind of maybe make my audience understand what the standard of model of physics is, and what are we still missing from it.
Right. So let's start at the top end. So today, what we understand about our universe is that it consists of 4% of the stuff that is all around us, which we call baryonic matter. This is just protons, neutrons, atoms, and all sorts of things that we know. Around a quarter of the universe, 25% or so, is dark matter, and we'll circle around to what dark matter could be. And of course, the rest of it, more than 70 odd percent, is dark energy. This dark energy piece is the thing that we actually have almost no ideas about. Okay, so the standard model of particle physics is like a periodic table. It explains this 4% of the world that we see all around us. The stuff like what my table is made out of, or what stars and galaxies and everything that we already know about. What are these things fundamentally made out of, and why do those things stay together? So these two things is what the standard model tries to address. So ultimately, if I break things down, where do I end, and why do these things stay stuck to each other? It is a remarkably successful theory, the standard model itself. And I'll tell you why this is a problem. The fact that it is successful, it is the only theory in physics that is tested over, like, 10 to 12 orders of magnitude. So it's a single theory that can describe phenomena that are happening at, say, 1 and 10 raised to 12. So that's the breadth of the standard model. This is great, right? We should be happy about the fact that we have a theory that's managing to explain all of this. Any experiment that you do, it gives you the right results, it makes the right predictions. The problem is, it only explains 4% of the universe. So the standard model doesn't really have an explanation for this, even the dark matter part. Forget about dark energy. That is one of the biggest things that is driving research in particle physics. We've known for a while that dark matter exists, and there is no dearth of ideas as to what we think it is. It could be this kind of a particle. We can look astronomically and we can judge what it is. We have not been able to create it in our colliders or find it astronomically. Like we have indirect evidence, but we don't have direct evidence. So my example of this is, if suppose like you're a school kid and you come home from school, there is tons of indirect evidence whether your mom is inside your home or not, right? You'll be able to see her chappal outside. You may hear somebody walking in the kitchen or something. So you have indirect evidence that dark matter exists, but there's no direct evidence that this is what dark matter is. And so this is the issue, that you have an incredibly successful theory. This theory is helping you predict everything about whatever you can do. If I want to collide protons, it makes the right prediction. If I collide electrons, it makes the right prediction. If I produce a kind of, like the weak bosons, and I see how does a weak boson couple to a top quark, I can ask like esoteric questions. All of this the theory manages to predict, but it doesn't tell us what dark matter is. And so this is kind of where we are stuck. So the standard model is really beautiful. It's an amazing triumph of science that we as human beings have managed a single theory that does all of this. But at the same time, it's also a tribute to our curiosity that, it doesn't stop there. We've managed to discover other questions that it can't address.
How interesting. Now you're part of the CMS collaboration, and the recent recognition was for the CMS collaboration. Will be great if you could explain that. And what does it mean to be part of a team of thousands of scientists from around the world? And how do you coordinate and agree on what do you actually look for?
Okay, so traditionally, particle physics started off with individual labs. So it would be a team of 4 or 5 people working in their lab, and there'd be a scientist somewhere else. As one discovered that one needs to move to higher and higher energies or more and more intense beams, the investment of money sort of goes up. So then it is no longer possible for one group or one university to do it, but it would need teams of 3 or 4 people. So this is how organically the whole thing has grown. Today we are at a point where the CMS collaboration, which runs the CMS detector itself, this is a fairly, it's an understatement to say that it's a complex piece of machinery. The number of active channels that it has is well into the 100 million, which means that you get 100 million numbers that come out of this detector. Each of these numbers means something different, and you need to put them together in the right way to make sense out of what is going on. At the same time, you have to keep the detector going as well. This is the reason that you need a team that is large and diverse. You need a variety of expertise across engineering, electronics, statistics, computer science. It's a sort of diverse set of skills needed to make sure everything goes smoothly. Now, when I started in the field, it is of course interesting, right? Like you start off, you have dreams that I want to win the Nobel Prize or something like that, and it was kind of eye opening to realize that the Nobel Prize is only awarded to 3 people at most. This means that the CMS collaboration winning a Nobel Prize is very difficult, which is where the breakthrough prize is actually a good recognition. So, how do you get, say, 1,000 scientists to work together? The things is, it's important to understand what motivates people to do science. It's curiosity. It is also the need to be independent. You want every scientist to feel that I have this idea and I want to pursue this, so you want to respect that. At the same time, you need the goals of the community to be met. You need the detector to keep running, and you can't have people be selfish. These two problems are solved by two sort of wonderful things that are sociologically today's multi science. One is that when we write papers, research papers, which is the primary output, everybody who's a member of CMS becomes an author, and the author list is alphabetical. This means that we have like 3,000 authors on a paper, and sometimes the author list itself is longer than the contents of the paper itself, but that's okay. So that uh, protects people from worrying about credit, right? They know that if they contribute in a meaningful way, they will become an author. So that's one good thing. The other thing is internal to CMS, we keep tabs of what are the things that the collaboration needs to have happen. For example, there are some tasks that a lot of people will want to work on, and there'll be some tasks that are difficult and less rewarding that not many people will want to do. So internally we have a system of points, and these points are assigned to different tasks. So if you want people to work on something, you give that task more points so that people will want to work on it. Now what are these points? These points are used to decide whether somebody should become an author or not. So authorship is linked to whether you can help and contribute to making sure the experiment runs smoothly. In when I say it out loud, it sounds like a rather harsh system, like you have to do this and only then you get to be an author. In practice, it turns out that uh, a lot of scientists like to work on difficult problems. So it isn't that hard to find people to tackle something that is challenging. Occasionally, you need to sort of rejig the efforts of the collaboration, but you do that by assigning tasks in different ways. The other thing that is important is that all groups of human beings which are large, like above 100, need a management structure. So even within CMS, we have a fairly good management structure. So the way it works is we elect people to be on top of us, and these elected people have terms that last for like a couple of years. So every 2 years you cycle through people, and we call them, so at the most part you call this person a convener, this because they convene a meeting. And so you elect somebody as a convener, then the convener sort of set an agenda and they try to drive the process, and every 2 years you cycle through that. um, it's surprising that it works as well as it does. If on the outside somebody had asked me that can you get 3,000 scientists to work together without arguing, without fighting, I would have thought that's a difficult thing to do. But this sort of keeps it going. You have to guard against certain things. You have to make sure the people who need recognition get it. For example, if somebody is looking for a job, right, these are the people who need to be able to demonstrate to their own institutes that they're doing good work. So internally, we have mechanisms to make sure that this is visible. It has to be visible that somebody contributed. There are internal awards. You can show these things also. So that's how you ensure that people work together, stay happy about it.
How cool is this? I mean, this gathering of 3,000 plus scientists, I think what we have missed out in the race of maybe like trying to build something is collaboration, because I think collaboration is always the key, because it's shown in swarm intelligence, such as maybe ants or honeybees and so on and so forth. And there are people who are working on AI, which is like which is kind of will have the same principles of swarm intelligence. So I think collaboration is the key, and it's the future. And I think the proof of the pudding was shown in during COVID, because that was the only time when I think all the scientists from around the world kind of joined hands. And that's the reason we got like a vaccine in a record time, which is like maybe just a couple of months. Normally it takes a period of like around a couple of years, 3, 4, or 8 years, depending upon the vaccines. So I think collaboration is the key. And kudos to this wonderful system which kind of helps everyone, and maybe pushes like, I mean, you said individual agenda also, and like a collaborative agenda also, to kind of push the main conversation of researching and finding a solution. Now you've also been part of finding Higgs boson, the so-called god particle. Maybe it'd be great if you could talk about that, your role into it, and what is this beyond standard model of physics. I mean, where it will be great if you could give a lay of the land of the beyond standard model of physics.
So okay, so about the Higgs boson, that's interesting. I was part of the Atlas collaboration then, not CMS. So I was a postdoc then when the Higgs was actually discovered, and I haven't directly worked on a search for Higgs. So the way I've contributed is in terms of figuring out whether the objects that are used in the Higgs discovery perform well, whether the simulation samples exist, and so on. So it has been a support role. But the discovery of the Higgs boson was one of the primary aims for why the LHC was built. So when the previous collider, the Tevatron, was sort of tapering off, we had started to see very tantalizing hints. Of course, nobody really knew what was going on, but there's always this hope that, oh, if I could collect 1 year extra data, or another year. Um, and so this was a big goal that sort of happened. One of the reasons the Higgs boson is special is that it has been predicted for a long time. Like from the 50s and 60s, the theory of this spontaneous symmetry breaking has been around, which predicted that there should be some sort of a boson that is associated with it. The problem was nobody knew what its mass was, which means that if you don't know what its mass is, you need to look everywhere. And that was the challenge of finding it. Um, it also, because of the nature of the Higgs itself, the Higgs talks to particles that have a lot of mass. Now, I tell you why this is sort of an interesting problem, because if I want to discover the Higgs, that means I need to study particles that have a lot of mass. But if I need to make these particles that have a lot of mass, I need a lot of energy. So in some sense, that's how it sort of becomes a harder problem than it needs to be. The Higgs itself is not that massive. In the standard model, there are particles that are there's the top quark which is heavier than the Higgs, but still that was why it was sort of harder to find. In some sense, one thing that people like to say was that the Higgs completed the standard model. A lot of the standard model sort of worked under the assumption that a Higgs will be found. There were other competing theories also, but this was the most, not to say easy, but this was the most natural way things fit together. And so that's why discovering the Higgs sort of completed the standard model. It makes sure that, okay, whatever we've been thinking about for the last 50 years sort of makes sense, sort of hangs together. And now this is great. This would mean that you would think that the standard model is complete. So then why do you need beyond the standard model? It turns out that scientists have a fertile imagination. One of my favorite examples of this is extra dimensions. There's really nothing that directly demands that extra dimensions exist. um, Laymen are for lay people, typically we tend to think of three dimensions because that's what our space is, 3D space. And scientifically speaking, we put time along with those three, and we have a four-dimensional space time around us. That's what we know. Now, nothing really stops us there. Why can't there be extra dimensions? And so, this curiosity is one motivation for say it would be beyond the standard model. The standard model doesn't require this, but hey, why not? Let me look for it. That's one example. Another example is the standard model tends to think of, for example, quarks and electrons and muons as fundamental particles, which means if I take an electron, I can't break it apart anymore. Okay, the theory works, all the calculations work out, and so on, but that is only at the energy that I've tested it so far. So who's to say that tomorrow, if I have a collider that sort of is as large as the solar system, and I'm doing these collisions, I won't find that an electron is instead made of something inside it. And that, of course, is not standard model, but that is beyond the standard model. So BSM physics, or beyond standard model physics, is this collective name we give to all of these fancy ideas that we have. Some of these ideas have good motivation, or they have a reason to exist. For example, dark matter. We've observed dark matter exists. Now somebody has to propose what is dark matter. This would be an example of a reasonably well motivated beyond standard model theory. At the same time, even our curiosity motivates us that why not this. For example, in the standard model, we have three generations of matter. So I have electrons, muons, and taus, or an up quark, a charm quark, and a top quark, or something like that. Um, why should we stop at three? Why aren't there higher generations? Now, this is just a curiosity question, and to be honest, nature has surprised us before. So there's no reason for us to feel that no, today we've discovered everything and life is complete. That's also motivation to do beyond standard model physics.
Right, right. Yeah. So, Professor, I mean, how? Because I think we humans are forever curious, and I think curiosity gets us to these big answers which are way beyond, and I think we humans should forever keep on, like nurturing the curiosity, because that's when we find things and discover things which are completely truly unique. You spoke about beyond a standard model physics. There are people who are working on something called as beyond space and time. There's a physicist called Nima Arkani Hamid, and there's Donald Hoffman, who and they say that the space and time, like at least Donald Hoffman says that the space and time, that it does not exist. It's basically like a virtual reality exists. And maybe during the course of the conversation, you also mentioned that when you're trying to kind of find like probe like an atom which is like really 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 small, you end up creating huge energy. So the act of meaningfully observing scales which are maybe smaller than a Planck length, the act itself creates maybe like black holes and things like that. So I think, yes, we are sitting in a fantastic point of time, and I think physicists, researchers such as yourself are probing these things, and I'm sure we'll get answers maybe which is much beyond than maybe what or true what we completely understand at this point in time. Now you mentioned that your universe is made of 4% is matter, 25% is dark matter, 70% is dark energy. Will you be able to kind of give us a lowdown on this, both the dark matter and dark energy, and what are the works that you are doing into possibly maybe kind of having an understanding of figuring out what this both this dark matter or dark energy is.
Okay, so I'll do good faith attempt at dark matter, and then I'll say what I know about dark energy, because that's where I'm really not an expert. Um, it started by looking at how stars revolve in a galaxy. Now, it's only gravity that matters. So what happens is, if I have a star going around the center of a galaxy, I can check the velocity with which it is going around. And what I expect to have happen is that as I look at stars that are further and further away from the center, they're going to be moving slower and slower, because at some point all of the mass is here. If I go from here to here, there's no other mass, so the speed sort of slows down. So you can make these graphs. What was discovered was that that's really not true. No matter how far out you go, the speed sort of stays constant, which means that there is some sort of matter that you can't see, but you keep getting more and more inside the orbit. That's what sort of triggered this. Of course, now we have more evidence. We have this thing called gravitational lensing, where mass acts like a lens, and you have light that bends around it that tells you that I can't see this, but there is a lot of mass here. Now that is what we call dark matter. Normally you would assume that there doesn't have to be a fanciful explanation for dark matter, right? We always start by assuming that it could be the stuff that we know. It could be like faint planets. It could be like red dwarfs, stars that are too dim that we can't see, and that's why we think there's all this mass. But you can do a lot of surveys and a lot of studies to do this, and it turns out that that comes nowhere near explaining the total amount that you see. You also see that, okay, this thing that is missing, it doesn't seem to glow like other stars. Now, glowing is a property of the electromagnetic force, or stuff that has charge can glow. Since this dark matter doesn't glow, most likely it doesn't have charge. So this is where now you're stuck. You know that this thing has gravity, which means it has some mass. It probably doesn't have charge. It probably doesn't interact in some of these other forces, like strong force, for example. So what is it? That's where we are. So this is why we have two sort of big hopes in trying to study dark matter. One is that we create it in the lab. So if you do these collisions, you're going to produce all sorts of new stuff. Hopefully you produce something that looks like a dark matter particle. We have a bunch of theories that try to have models of how different kinds of dark matter would look. So fine, that is one approach. The other approach is that we have the Earth goes around the sun, and the sun goes around the center of the Milky Way. So presumably we are going through this dark matter always, right? So if I have a detector on Earth, sometime I should see some dark matter interaction. And so that is what a direct detection experiment would be like. And so these are the experiments that we're doing to study dark matter. Dark energy, on the other hand, is not even particle physics. It's more like a cosmology problem. So when we study the universe, one of the important things that we want to know is that the speed with which the universe is expanding, is this speed of expansion slowing down, or is it speeding up? If you think of a regular sort of an explosion, right? Like if I have a bomb explode, usually what I know is that when the bomb explodes, the particles are moving very fast. And then over time, they're going to sort of slow down because of friction and this and that. And expansion will slow down. That's what you may think about our universe. It turns out that what we have seen is that the universe's expansion is actually increasing in speed. So the expansion is happening faster and faster. That means that there has to be some reason where this extra energy is coming from, and that is what we are calling dark energy. We really don't have a lot of ideas about what dark energy is. Of course, the cosmologists do, but there aren't a lot of experiments right now which will probe what dark energy is. Um, the thing is also, at some sense, that it plays a role only at cosmological distances and times, which means that it's really hard to do a tabletop experiment to study what this thing is. That's the only reason we haven't made a lot of headway. Theoretically, we have a lot of wonderful ideas. The issue becomes on the experimental side. This is where, in some sense, I think the fact that we now do gravitational waves, this is really important. So the fact that LIGO can see displacements that are as small as 1,000th the size of a proton, this is humanity's incredible thing. But now that means we've opened up this window into being able to observe gravitational waves propagating from very, very far away. And that opens up a new way to look at the universe. So hopefully, since dark matter and dark energy both in some sense do gravity stuff, studying gravity in detail would be a good thing. And so there's a lot of hope that I have from, for example, these gravitational wave experiments.
Professor, I mean, I'm just going to push a little bit more on the question I kind of asked earlier. I mean, obviously, I mean, the goal of LHC is to kind of figure out the Big Bang, how we all kind of originated from, and the entire universe. And through this course of the conversation you mentioned, I mean, we have like a certain understanding, but there's so much more that we need to kind of understand to have like a complete understanding of the entire ingredients of I mean, how, when the universe was kind of made of. What's your assumption or intuit over there? What do you think we might need to maybe have like a complete understanding, not just the dark matter, but or even the dark energy? What would be the breakthrough that's required, maybe 100 years, 200 years? What's your intuit over there? What's the roadblock that maybe is there, which is stopping us from us maybe probing and completely understanding? I'm sure once we do that, maybe we humans will be godlike. But what's that roadblock that you see? And maybe if you could also maybe elaborate on the beyond standard model of physics. What is it that I mean, you're looking for? Maybe are there extra dimensions? Are you trying to unite quantum gravity through standard model physics? What's the, like, what's the core this thing experiment what you're looking for with beyond standard model of physics?
Okay, so to tackle the first question, if I had to sort of place bets or guess, right? Being an experimentalist, I'm fairly cautious with this, but okay, let's throw caution to the winds. Uh, One of the things I'd say is that, in my personal opinion, all of the richness of nature that we see around us, right, from biology, chemistry, all the way up to stars, and we have like these fanciful things like neutron stars and so on, quasars, etc. All of that we have managed to understand by just this 4 or 5% of the universe that constitutes the standard model. This 25% dark matter, for sake of convenience, a lot of scientists tend to think of it as some new particle. But if I'm being honest, 5% of the universe is so rich and diverse and full of all sorts of crazy stuff. 25% is going to be even crazier. I think the really, really big deal is going to be when we open that door. So at the moment, the fact that we don't have any insights experimentally into what this dark matter particle could be, once we open that door just a little bit, it also helps that for a lot of theorists, right, you need to be able to come up with good imaginative ideas. But you can only do so much before at some point you need an experiment to sort of tell you that is this on the right track or are you completely off base? And that is what has been missing a little bit. I feel very comfortable in saying that as soon as we pick at this door a little bit, we have a first idea of what dark matter sort of is. A lot of smart people are going to have wonderful ideas about probing it a lot better. Um, See, in some sense, tech is the problem always, right? Like, as human beings, can you make something bigger? Can you go to higher energy and so on? So that, of course, has to happen. And tech breakthroughs are drive a lot of science. Like, if I can collide things faster without having to build a bigger tunnel, or I can actually build like a collider that circles the moon, there's stuff like this. If I can do that, if I can solve the tech for it, that is kind of important. So that was the first thing that I think we should try to do. I'm really hopeful it happens in the next maybe 25 years, not even 100 or 200. Uh, as to beyond standard model, so now let's come at it differently. What is it that the standard model is unable to explain? So the standard model doesn't say what dark matter is. The standard model, actually, in the standard model, neutrinos don't have mass. But we have now discovered that neutrinos do have mass. So we need to understand why that is. And the third thing is sort of an interesting problem. It's called the hierarchy problem. There are various ways of formulating this. I'm going to do a quick thing of how to formulate it. Just one example. There are other ways of doing this as well. So suppose you and I both decide to write down two 4-digit numbers. So you will write down a 4-digit number at random, and I'll write down a 4-digit number at random. Okay, without talking to each other. Then we sort of compare our two numbers and we subtract them. How many digits do you think the answer is going to have? So my 4-digit number, I'll say, is 8152. What is your
Right.
number?
1379.
So if we subtract these two numbers, the answer has 4 digits, right? Okay. Now suppose we did the same thing with 6-digit numbers. Let's not do it, but if you and I both wrote down 6 digit numbers, typically the subtraction is also going to have 6 or 5 digits. So that means that if I take two 10 digit numbers at random and I subtract them, I get a 10 digit answer. All right. The Higgs boson, if I try to write down a theoretical expression for the Higgs boson, it turns out that the Higgs boson in our units is a 3 digit number, 125 GeV. The corrections on the right hand side of this expression are large numbers, 10 digit, 12 digit, 14 digit, 16 digit numbers. If I am randomly adding and subtracting these large numbers, what are the chances that I'm going to get a 3 digit number as the answer? That's really, really difficult. It's the same as saying that suppose you picked a 4 digit number and I picked a 4 digit number, and the subtraction was only a 1 digit number. Like you picked 1739 and I picked 1740. That would be very, very unlikely. And so this is in some sense a formulation of the hierarchy problem, that what we see in our universe right now, the Higgs and so on, seems to be very finely tuned. I mean, I don't want to go down that road, but it's as if saying that somebody has tuned the knobs on a radio for to get precisely the right answer. And so now, how do you explain this? The thing is, to explain this, you can have a bunch of different ideas. So one idea is the idea of extra dimensions. For example, I worked on a black hole paper that sort of stemmed from a paper that Nima and a couple of his collaborators had written. There is the idea of supersymmetry, which was, for example, my PhD thesis. So, supersymmetry, one of the big things it does is it also explains the hierarchy problem, gives you a dark matter candidate. There are other theories that sort of manifest from there. What we've seen is that historically, electricity and magnetism used to be thought of as two different things, but now they sort of merged. We've also now realized that electromagnetism and the weak force also sort of unite. And so this is why we have this feeling that in all the forces unite somewhere. We have these grand unified theories. And so that is another reason to do beyond sand model. So an actual beyond sand model theory is going to make some concrete prediction. It's going to say that I want to solve this problem. For that, I predict that this kind of a new particle should exist. Then it is the goal of the experimentalist to go look for this particle, look for whether it exists, can I find it, and whatnot. And out of all of these potential new theories, try to pick out the one that is right. So that's what I'd say. So there are a bunch of these new beyond time model theories. Not all of them necessarily are as well theoretically motivated as you may think. Like some of them are mathematically very sound. Some of them are mathematically educated guesswork, because, for example, we don't have all the right theories in place. For example, we don't have a quantum theory of gravity. We have ideas. We have ideas about whether it should be quantum loop gravity, string theory, and so on. But we are not really sure. This means that if a theorist has to write down something concretely, they have to put in some educated guesswork, some assumptions, something or the other. And so that's what I mean. Like, not all of these new theories are theoretically equally sound, but they're all good ideas for what nature could be doing. And so the problem really is that it's not that I don't have a lot of good ideas, it's that I don't know which good idea I should pursue. So
In the course of the conversation, you mentioned about the fine-tuned universe, and I think that is something I think everybody is kind of scratching their head. Some of the top physicists, how is that even possible? I mean, there are things which shouldn't exist, seamlessly in this universe. Is there maybe do you think about that? This fine-tuned universe maybe would be great if you could share your thoughts on that. And your work, a lot of your work focuses on something called as jet substructure. Will be great if you could explain that to us, please.
okay, so about the fine tuning problem, in some sense, this is what a lot of science is, right? All science at its fundamental level is trying to explain nature. So if I walked into a room and I saw this pencil sort of standing on its point like this, I would want to understand, I would look for an explanation, in the sense that this is not stable. Is it stuck to the table? Is it hanging on a thread or something? So science is the need to understand phenomena. It would be easy for us to say that, well, okay, so the universe is fine tuned, so what? So it just happens to have the right parameters, so what? That's not what a lot of scientists like. We like to look for, reasons, like, okay, why is it this way? So that's true for me as well. It seems like giving up to say that, well, it is the way it is because it is the way it is. That's not really an answer anymore. Then let's come to jet substructure a little bit. So the Large Hadron Collider, as the name suggests, you tend to produce a lot of hadrons. So hadrons are bound states of quarks that exist. And it turns out that you can't actually have a single quark or a single gluon exist. They always need to exist in these bound states. So what happens is at the LHC, you produce a single quark or a single gluon, but before it comes out, it sort of turns into a bunch of hadrons. It's like a spray of particles all going together. This spray of particles is what we call a jet. So a jet basically consists of a spread of these particles going like this. Um, Now, you can get this spray of particles because of any kind of underlying quark, an up quark, a bottom quark, a top quark, and so on. Jet substructure is the idea that I'm going to look at the spray of particles and not just the entire jet, but I'm going to peek inside it to see if it has certain structure inside it that allows me to tell what was the originating particle. Did it come out because of a W decaying to two quarks? Did it come out of because of a gluon? So this is why this jet substructure field exists. It is a very rich field because, as it turns out, QCD, or the strong force, quantum chromodynamics, is something that is rather hard to study. Unlike, say, electromagnetism, which is the force that we are all most familiar with, when things go apart, the force becomes weaker, right? And as you move them further apart, they become weaker. This is nice because this means that if two charged particles are really far away from each other, I can sort of say, look, they're not really interacting anymore. It's very weak. The strong force is the opposite. When things are really close to each other, it's very weak. But if two things are further away, it gets stronger and then stronger and stronger. So that means that when you go to extremely high energies, that means you're going very close, the strong force is very weak. So you can't really, you can study it, but it's not really telling you the thing. You need to study this at lower energies. And lower energies means inside these hadrons and inside these jets, which is where the strong force rules. So I'd like to share a good example with the audience. So if you take a proton, people will tend to know that a proton is made up of three quarks. So in some units, the proton's mass is 1000. So it's like 937 MeV. Let's say it's 1000. If I add up the masses of the constituents, that adds up to 10. So out of 1000, only 10 is explained by the fact that the proton has three quarks. So where is the rest of this 990 coming from? Turns out that the rest of this 990 is just the strong force itself. It's the binding energy of the strong force. And if this sounds weird and difficult to comprehend, it is because it precisely is. QCD, or quantum chromodynamics, is so complicated that even in PhD level courses of particle physics that I've done, we will do QED calculations but not QCD calculations. They're only reserved for people who are working in the field. So this is something to study well. One has to study jets and jet substructure because that's the window in which we can study the strong force. And if you study the strong force, it's a big part of the universe. This allows us to circle back to something else. So we like to say that the Higgs boson gives mass to everything. And this is true. I mean, all the fundamental particles get mass because of the Higgs. But if you look at you or me, most of our mass comes because of the protons and neutrons that we have in our body. And most of a proton's mass is actually the binding energy of the strong force. So I could just as easily say that most of the mass that we see around us is actually because of the strong force, not because of the Higgs. So this is why it's really important to study it. Jet substructure is a very important tool that allows us to do that. Another reason that this allows us to segue into a different topic, like one of the reasons jet substructure is a also popular thing to do is that it is very amenable to machine learning and neural networks and algorithms like that. Because you have a lot of data at the LHC, you can apply a lot of these modern AI techniques to things like studying jets. And that is also why the study of jet substructure has somewhat exploded. It is not necessarily always deterministic, but it's also learned in the sense of a neural network learned.
Right, right. How interesting. And I think, I was just about to kind of get into, AI and machine learning, because you mentioned about these jet substructure, spraying so much data, unimaginable amount of data. How is this, the role of AI and machine learning changing the game? Because, at this point in time also, I mean, there is the entire world is caught with the hype of artificial intelligence and machine learning. And I think possibly we are the cusp of maybe something called as artificial general intelligence. Maybe we'll get into that, but it will be great if you can elaborate on this the data that LHC kind of produces, and the role of AI and machine learning over there.
So the simplest way that AI started off was pattern recognition. And it turns out that like the name neural network suggests, our eyes are wonderful pattern recognizers. So I don't know if you know this. Like we've had these things in the past where people will have a cloud and they'll see that I see Ganesha in the cloud, or I see Jesus in this piece of toast, and we've had this. This is because our brains are wonderful pattern matchers. We tend to see patterns in things that where there aren't any, or where you can find the faintest of patterns. What a neural network does is that it allows you to do this to numbers that are not just in your head but actual numbers. And so this is where the marriage of AI and particle physics sort of happens. That we naturally have a lot of data, we have a lot of numbers. We are aware that there are patterns within these numbers because we understand the underlying theory. It's just that if I have, thousands of numbers, then by hand I am unable to find a pattern. This is where AI comes in. This is how it all started. Um, so particle physics has been an early adopter of AI. I remember even when I started my PhD a long time ago, 20 odd years ago, we already had like uses for this. Now, what has really changed in the last 10 or 12 years is the barrier to entry to do some sort of AI has gone down very drastically. Google has this wonderful TensorFlow library, and there is Google Colab where you don't have to know anything. You can just download some packages and play around. There are tons of blogs on data science and Medium and whatnot that talk about how you should run your own simple neural network. This means that you no longer need to be a mathematical expert or a computational expert to run your own neural network. The barrier to entry has gone down. What is nice about this is that, see, the smartness exists in different fields. If I had only a smart mathematician who could run a neural network, then the ideas of using that neural network are sort of limited. Now what I have is I have a smart artist who has access to AI. This means that you can imagine different uses of this tool. You can think of different ways in which you can solve these problems. So in some sense, this is actually quite wonderful that the barrier to entry has gone down. There are of course cautionary tales. It's always natural that access to a tool that is that widespread can lead to a lot of sort of interesting things. Instagram, for example, keeps pushing these AI chatbots now, which is a bit. I mean, maybe it's not necessarily a bad thing, but as long as people are educated about it. So in particle physics, now the use is extremely heavy. So much so that being a physicist, I still taught a machine learning in physics course here at IISER. It was a sort of a module course. The idea is that people can use this a lot easily. At the very least, people should be able to become users of AI, if not developers. They need to understand what the ins and outs are, what it is good at, and what it is not good at. Once you know that, then that's true of any tool, right? Then it just becomes a tool like any other tool.
True, true. Professor, you've been vested in AI and machine learning. Now there's this global race of some of the top companies in the world, even nations, racing towards developing artificial general intelligence. Machines which are possibly maybe having the same level of intelligence, such as maybe humans. Now there is various approaches that people are kind of working towards. There are people who are trying to kind of reverse engineer the human brain, and there is people using maybe something called neurosymbolic AI. There's also people who are working on something called as physics, which is grounded in AI, which is grounded in physics. Embodied AI. What's your intuit? Somebody who's been working on this for the longest time, using AI and machine learning, LHCs. What could be that pathway which you think could get us to machines which has a human level intellect and beyond, what they call artificial general intelligence?
So I'll start with this interesting thing. So I've grown up liking a lot of Isaac Asimov. So I read a lot of his robotics books and so on. There is a travesty of a movie called I, Robot, which really didn't get the point, but it has a really nice exchange between Will Smith and the robot in the movie. Uh, the robot, which is an example of AGI, has been caught in some crime, and Will Smith is the policeman interrogating it, and he asks it that you're just a machine. What do you know about, can you paint a sunset, can you write a Shakespeare sonnet, can you write a song or a symphony? And the robot replies to him and says, can you? And this is true. There is a significant overlap between uh, what humanity, all human beings can do, and what AI can do already.
True, true.
Already AI can do a lot of things that I can't write a symphony, but there are models out there that can do this. which means that how I define AGI is kind of interesting. So for me, the way I'm looking at this is that at some point, it's indistinguishable from some sort of a human. For example, if it's smart enough to mimic the behavior of a 5-year-old kid, then at some, is that, has it passed the test? Is it AGI already? And human beings to a large extent learn by, patterns, basically rote learning. This is why when I'm learning a new language, people say you should do immersion. You surround yourself by people who speak that language, you start repeating phrases, and that's how you learn. This is what today's AI is already doing. A lot of chat GPT says regurgitates information that it has read. Who's to say that if I have enough connections that are available, it won't at some point start mimicking AGI, or I mean, mimicking a human being's intelligence. So in some sense, it's a very tricky definition as to what I'd call, you know or when I'd say I've crossed the barrier into saying this thing is actually human like intelligent. There are a lot of things it can already do that human beings can't. So in some sense, it's a very, it's ill defined to say that, okay, this was the point at which we crossed over into saying now it exists. I think a lot of people, what they tend to think of is in terms of robots. They assume that an AGI means that I have some other being that I say you run my household and it knows what to do without me giving instructions. We are maybe not that far away from that, because if you think about things like smart homes, or Siri, for example, managing your appointments, it's there to some extent. Sure, it makes a lot of mistakes and it needs a lot of hand holding, but anybody who's had, like, help knows that that's true of human beings as well. So
Rightfully pointed out, I mean, these LLMs are pattern matching machines, and so are we in some ways. These LLMs hallucinate, and so do we. I mean, my wife, I mean, if you ask her about an incident, and she'll, to every different group of people, she'll paint it a little differently,
that's it.
unknowingly, and she, so
Exactly.
we
That's memory.
all,
Yeah, memory recall
yeah,
is that. Yes,
yeah,
yes.
we all hallucinate. And you also pointed out these, even these statistical models, I mean, it's very, very surprising. These are data and data out models, but they are even now showing these emergent properties. There have been papers already about how these large language models, statistical models, data and data out models, they have these emergent properties. There have been instances of, I mean, these models faking alignment, or showing self-preserving behavior. So yes, I think, there is, I personally feel, and like, maybe, like, people such as Demis Hassabis and maybe Sam Altman and Ilya Sutskever, that there is still possibly that even maybe scaling could be the approach of building artificial general intelligence. And maybe we might not need like a novel architecture, but yes, that doesn't mean that we shouldn't, because I think the world, there are so many people at this point in time who are working on maybe possibly figuring out what that novel architecture could be in developing maybe, some this
So since you said that, I'd like to say that I'm a particle physicist, which means that in some sense the model that particle physics follows is reductionism. So you try to break things apart. You say that all of the properties that I observe, I'm going to do these properties based on how these things fundamentally interact with each other. So if I have two individual particles, how these two talk to each other, and that's where I'll build things. But this is true that a lot of science doesn't consist of individual things that you sum up, but they consist of emergent properties. Like, emergent is the real, important word. When you have something of scale, then the sort of things happen can't be predicted if you have just two of the thing. And there's a lot of physics that is not particle physics that deals with emergent stuff. Like, a lot of condensed matter physics, a lot of statistical physics deals with these emergent properties. And it's who's to know that artificial intelligence isn't actually an emergent property once you just reach a certain scale. This is true.
True, true. So, Professor, you are the professor at one of the India's premier science institute. And today I think the world is completely changing. With this convergence of like artificial intelligence with AR, VR, MR. The education itself is kind of changing. We are going from maybe like a traditional learning to something called as personalized learning. With AR, VR, MR, we at the cusp of possibly immersive and experiential learning, because you mentioned about rote learning, but I think the only way we learn is when it's experiential based. Will be great if you could kind of paint a picture of what the future of education is going to look like with this convergence of tech stack.
So there are two things. Like, we've already realized that you need to take an LLM and you need to marry it to some sort of fact checking. Now there are already other smaller engines, not ChatGPT, but something like SciSpace or whatnot, where the fact checking part is tuned up a little bit. Now once that is in place, I see no reason why something like this could not be used for an education tool. Most of the time where we struggle is that if you have a large class, right, the teacher is unable to give individual attention. This is fine. So the model that I sort of envision is that the instructor does a core thing for the whole class, but now each of the different people has a slightly different doubt in their head. It's sometimes impractical for each person to be able to talk to the instructor and say that, which is where a lot of sociology and psychology comes in. That children tend to be sometimes have inhibitions, sometimes they don't want to appear stupid in front of their friends, all of this. A lot of this is what this AI based education can solve. It is where, individually, if I can ask somebody or some object, that solves the problem for me. um, One of the things where this is going to be tricky is that a lot of oversight is going to be needed even in these sort of things. That either you control the LLM or you control that object very tightly into what information it's giving out. um, because in the education sector it is sometimes very hard to undo mistakes of the past. For example, let's stick, not even do like history or geography, let's just stick to physics. If you teach somebody a wrong method to solve a problem that works in just a specific problem, the thing is they've learned this and now they're going to keep reusing this over and over. For them to unlearn that is difficult. So as long as the AI tool is something that you periodically review or you stress test it, I think it's something that is going to be fairly ubiquitous in education, if not formally, then informally. For example, you can't stop winds of change. A lot of students already turn to a lot of these tools and they have creative uses for this. So even at IISER, for example, now we actually have a AI committee which is looking into what sort of different uses we can do, how you can incorporate this in your classroom, what sort of exercises you can do. And so that is already something that we are sort of actively trying to see. Can we help instructors use this in a judicious way? Can we tap into what the students really need? I don't think they necessarily. So there's two ways to this, right? One is in trying to help the student learn better. The other is in trying to reduce the work of the instructor. So, for example, you can use AI to say assess papers. That is where I'm a little uncomfortable about. As long as the education is going to the student, that's okay because students are smart. They are also able to take in three or four different sources and judge them. If it's assessment, on the other hand, that's more of a thing where you give some marks, but if you don't look at it carefully, that can be a little dangerous.
Right, right. So thank you, Professor. I've just got like, I mean, two or three questions. I mean, and I'll try and kind of finish it up quick because we're running short on time. So reality, the movies such as Matrix, it show the core concept of the movie is that reality itself is not real. Then the quantum mechanics, the Copenhagen interpretation, it says that the consciousness brings up a conscious observer brings up reality. Then we have something called a double slit experiment. Which shows that the photons they don't exist. I mean, you mentioned that we are made of photons and neutrons, and the entire universe is made of these particles. What's your thought on the nature of reality? Would love to get your thoughts on that.
So some of my thoughts are shaped by the fact that I'm an experimentalist, which means there are two things. It's sort of very tempting to imagine that we are in some sense the center of the metaphorical universe, and thus what is real is merely a matter of what I perceive or what I build. Um, I don't believe in that. I do believe that there is objective reality which exists, and we as human beings make some sense out of it. Now, it is true that all of our experiences are shaped by the fact that we are human, which means we have five senses. We tend to look at the world through this, and so that's how we build a picture of reality. Um, where some of this for us can be solved is the fact that sure, I do build a picture of reality in my head based on being a human, but we have the tools, the mathematics and the physics at the moment to predict, okay, I have some remote star there and I have a remote star there. I'm able to model their interaction. Now, there is nothing that I am doing that can influence that interaction. It's very far away. It's happening in the past and whatnot. This is what makes me believe, in some sense, that there is a reality that exists outside of us. It is true that not all of it is something that we are able to explain. I mean, sure, we are limited by ourselves, right, by what we perceive. So there are some things that we model exceptionally well. Um, there are some things that we may not be modeling at all. Uh, this is something that the dark matter thing sort of comes back to when I talk to students about this. Today we tend to assume that dark matter at least has some sort of interaction with regular matter, so I can feel it. This also ties into the concept of ghosts, for example. Imagine that you have a ghost, but that ghost has no way of interacting with material things. If it has no way of interacting with material things, then how does it matter? You're never going to know it exists. This is true of dark matter also. If dark matter does not have any interactions with regular matter, then large amounts of dark matter could be around me in this room, could be streaming through the earth and whatnot. It just would not do anything. So it is true that there is a part of reality. I mean, I think reality is objective, but I don't think as human beings we necessarily have the ability to grasp all of it. We are limited by what we can observe and by what our math and what our inventions and discoveries are. So we do grasp a part of it that seems to be real enough. Um, but there's bound to be stuff that exists outside of it.
Professor, really, really appreciate you taking time being part of the podcast. My last question to you: what's your moonshot? What are you going after? And will be great if you could give your thoughts on cosmogenesis. Something which Alan Guth kind of push forward that universe in a lab. And then I had this privilege of also interviewing Professor Eduardo Gondelman from Ben Gurion University, and he's been like I mean. Thinking about and of the idea of cosmogenesis, the idea that theoretically you could kind of create a universe in a lab, and your expertise also happens to be like a mini black hole. Will be great if you could maybe talk about your moonshot, what comes next for you, and the thought about this, like creating a universe like we know in a lab, cosmogenesis.
Okay, so this is actually a good question. So Moonshot for me is going to be, see, one of the problems with having like these large collaborations is that everybody is thinking of the same thing, so everybody is trying to do something. For me, the moonshot recently has been we need to have some discoveries that are new. We need to have some information of what beyond standard model physics is going to be. So I'm trying to at the moment work on things where I'll do a literature survey, and if there are no papers that are talking about it, I'm very happy. I'm like, okay, that seems to be something that nobody's addressing. We need to look for all of these corner pockets where somehow the light has not reached. Somehow, that aspect has been ignored for various reasons, for fashion, for whatever. That's what I'd like to do. um, I think the cosmogenesis idea is interesting and is also a little bit scary. This comes also because of the Higgs boson. So the Higgs potential is something that is thought of as a Mexican hat. Okay, so the idea is that um, in quantum physics, we have this notion of tunneling, where a state can overcome a barrier and go to a lower energy state. Um, this is true of our universe also. So we are, for example, we don't know if our universe has access to a lower energy state and it can tunnel at any moment. Um, when I had first heard of cosmogenesis and the idea of trying to do some of this in the lab, that was the scary part. That okay, so suppose you set off some bubble. What does it mean to the universe we live in? Um, I think this is it's above my pay grade to, to some extent. It's a difficult thing. I wouldn't say that it is more viable than some of the other crazy ideas that we have out there. It is certainly something that is worth really thinking about. When the LHC was built, for example, there were a lot of people who were worried that this is going to destroy the universe. And as scientists, of course, we fought it and so on. But I can understand where that fear comes from. It is the same fear we would have today of trying to venture into the unknown. You don't know if you're going to end up doing something that you really shouldn't have done. But I don't think that human beings think that way. Curiosity is always the king for us. We always want to know the answer, even if it's going to hurt us. So I'd stick to that. Like that. That's what is true, even of the cosmogenesis thing.
True. Professor, really, really appreciate you taking time and being part of the podcast. There's so much I got to learn, and I'm sure there's so much the listeners will be able to learn about this fantastic universe that we live in, and how we are probing one thing at a time to kind of understand what this beautiful universe, or and us, what are we made of. And eventually, maybe someday, because of people such as yourself, scientists such as yourself, maybe we'll truly understand what the universe is made of. And not just possibly understand, maybe once we understand, there'll be these loads of applications. I think the world wide web was like an output of LHC, and so was AI and machine learning, was the one.